All right, our next speaker this afternoon is Burke Banner, who's joined us this summer from UCLA. Burke's been working with Casey, and today they'll tell us about their project together, measuring the eccentricity distribution of binary stars using eclipsing binaries.
Thank you for the introduction, Glenn. So getting straight into why I'm measuring these eccentricity distributions is because eccentricity is a direct probe of dynamics of these stellar systems. So that means that by understanding eccentricity very well, we very much are able to simulate binary evolution and binary formulation of these binary stars, which is important for us to understand the interactions between things like circumstellar disks, which I have an animation here of, and a 3D model of. The overall idea behind having confidence in eccentricity comes from this, is the fact that we want to better understand how these binary stars evolve over time, the environment that they came from, and overall how they turn into more exotic objects like compact mergers, for example. The issue is that we do not have that confidence in eccentricity at the moment. So as you can see here in this graph, in blue is plotted Gaia's measured distribution values of these binary star systems. And in pink are values coming from the literature. So as you can see here in orbit, magnitude, as well as distance, Gaia and our model are actually are rather close together. It's a good fit, we would say, for the literature. However, turning your attention to here in this eccentricity plot, we see that there's a gap between Gaia's measured values and our modeled values. This is a problem because we don't know exactly where this discrepancy comes from. My project is in an attempt to create another eccentricity distribution to compare to Gaia's measured values and our current models to determine, okay, well, where should we go with this in evaluating the actual eccentricity distribution we should use in simulating these binary stars? So as I mentioned just now, we are looking for a way to understand this discrepancy. First, we need to note that we need eccentricity measurements independent of Gaia. The purpose for this is that we want a different selection function than Gaia, as that'll give us more unique, as that will just give us unique eccentricity values of these binary stars. And so because of that, we opted into using Kepler-found eclipsing binaries to obtain eccentricity values. The issue, which will give us a different selection function. The issue with this, however, is that Kepler is a solely photometric mission, and these binary stars are very long period. That means we don't have as many points of data for the light curve eclipsing. And so because of that, these binary stars were actually reobserved with the Keck telescope. And what I'm doing is I'm obtaining radial velocity measurements from the faintest targets that were found with Kepler using the Keck Planet Finder. 25 systems to be exact. So how am I obtaining radial velocity and how are we getting to eccentricity? First, we start with cross-correlation functions. So what are cross-correlation functions? I will build up to that. So first, what we have here is we have a normalized spectra, observed normalized spectra in orange, and in blue, we have a template spectra. And so the idea is that the spectra we observe is Doppler shifted. And so because of that, the absorption lines will be in a different location than where they should be for the same spectral type star. So what we do is we shift that spectra on top of the template spectra, and shifting the wavelength of the spectra results in a corresponding radial velocity. And then when you minimize the differences from these two spectra, you obtain a chi-squared function, which is an arbitrary y-axis value plotted against radial velocity. Or when you actually maximize the similarities between the spectra, that is how you obtain a cross-correlation function graph. So going into some terminology, this is a cross-correlation function graph, and it has 3 cross-correlation functions on it. The primary dip corresponds to one star consistently, and the secondary dip corresponds to the second star in the binary system. And what this is exactly is this is one observation of one system. So in this system, for example, we have 9 separate observations. So there are 9 total graphs that look just like this. I'm just showing one for clarity's sake because I shouldn't have 25 graphs on my slides. Anyways, um, the reason why there are 3 different cross correlation functions is because the Keck Planet Finder, in their instrument, they separate the orders into orderlets. So these 3 orderlets come from the same spectra. It's just divided in 3 as a way to obtain more values. So what I've been doing in my project is I've been writing a script that automatically fits these primary and secondary dips to parabolas and obtains a radial velocity value. In doing this, we were very happy to see that in most of these graphs, the radial velocities actually overlapped with one another, and that the errors from these values were indistinguishable from each cross-correlation function. And so because of that, we were like, hooray, there is no difference between these 3 cross-correlation functions. And in a way, they give us the same radial velocity values. And so because of that, we opted into averaging the 3 cross-correlation values. And the reason for this is because we figured, well, averaging it will even at least a little bit increase the signal-to-noise ratio. And so by doing so, we obtain a better radial velocity plot. And so it is these radial velocity values and their errors that turn into this radial velocity curve graph with radial velocity on the y-axis and the orbital phase plotted on the x-axis. Now, this isn't eccentricity, and we could theoretically obtain eccentricity by fitting a curve to these radial velocity plots. However, if you'll notice on the x-axis, these radial velocity values do not span the entire orbital phase. This is not ideal because since we don't have values for the entire orbital phase, we can't give a as confident value for the eccentricity. And so because of that, we turn to what will be the next steps and next portion of my project, which is jointly modeling these radial velocity values with light curve data. How we're going to do this exactly is, well, in eclipsing binaries along our line of sight, when these binary stars are furthest away from one another, their radial velocities are maximized with one moving away from us and one moving towards us at its highest speed. And when they're actually eclipsing, both of their radial velocities are at 0. And so in knowing this, we figure, okay, when our radial velocity curve is actually at 0, that corresponds to this eclipse or this eclipse. And so the idea is that by jointly modeling both of these data sets, we will obtain eccentricity values, which we can then use as parameters to then use as a baseline for a simulation to obtain another eccentricity distribution, which will then be used to compare to Gaia and our current model. Thank you.
Question for Burke. Every time. Anna is the most bold. Yeah, so I was wondering whether the orderlets are overlapping in wavelengths. The reason why I'm asking is if it would make, if you would be able to further beat down the noise if you just stitch them into one long spectrum and then the cross correlation on that rather than 3 separate chunks and then average them.
Yeah, me and Casey actually talked about this, me and my mentor. They overlap, but just barely, like at all. I believe it was like 0.0033 angstroms. So it is a very small overlap. So we decided we don't really have to think about the wavelength overlap in that sense. Yeah.
Thank you for your presentation. I really enjoyed it. I was wondering how you picked the 25 samples of eclipsing batteries to explore further into.
Right. So I'm working on a subset of these binary star systems. So I'm just looking at the 25 faintest that we happen to have gotten from Kepler. It's not so much that we chose these stars or these binary systems specifically. It's more so just that we chose binary systems from Kepler as a way to obtain a separate eccentricity distribution that doesn't have the same bias as Gaia or our current models.
the times that these were made? For example, for this one of them is the primary dip.
Yes.
One of them is the secondary dip. Like how far, like how long is the orbital period of this system? And like, is it like these are like very favorable periods of these systems? Like, are these the best like 25?
Oh, yes. So I believe this system is 63 days, but with all the binary systems I'm working with, they vary from 50 to 500 days. Yes. Mhm.